Not yet, not yet. Okay, I hope you have everything. I think we are mostly done with the Neumann function. It's just a little bit other properties that are very straightforward. So we've done the most difficult part to get the series. It's not exactly a series solution because of the log function, but I mean it's close to a series solution. And so the next equation is simple. It's just setting the order equals to 0, just y sub 0. And because that simplified, at first you don't have that inverse power of x series, so that get rid of that, and then the other series becomes the two digamma function becomes the same, and then you can use the expression for the integer argument for the digamma function and write it equation 14.62. So it's fairly straightforward. The next one is another integral representation, which should be a homework problem. So 14.63 is part of the homework problem. Either this homework and the next one, when we talk about the Hankel function. The Hankel function allows you to see how you get the form 14.63. So which is cosine. Let's just write it down because there'll be a similar expression for the j sub 0. In this case, the y sub 0 x is, we have this minus 2 pi cosine x cos t dt. Right. And then there's a second form, which is just based on a change of variable. From the first one, this form, and then you can do a change of variable to get the second form. And the derivation of that, I think, is another homework for the Hankel function. But anyway, it's related to the kind of j sub 0 and y 0. You can in the next section we'll talk about that. You combine them to Hankel function. So it's just like you have e to the ix, you can get the cosine x plus I sine x, so that kind of thing. So, so the similar expression for y j sub 0, I guess, is this is cosine, the other should be sine, and I think that's a change of sign also. That becomes sine. Right. And the zero order is simpler. There are other similar integral representation of arbitrary order, but those are more complicated. There are other terms in those expressions. But anyway, that's the equation 14.63. The recurrence relation is also a homework problem. So you work on that. It's fairly simple. Just use the definition of the Neumann function and show that the Neumann function satisfies the same recurrence relation as the Bessel function or J function. So that's simple. And the next one is the Wronski. We already done that. Last one is how to what is the situation you use the Neumann function. Basically, we don't use that if we have a cylindrical problem. If you have a cylindrical problem, and using cylindrical coordinates, so you have rho, y, and z. If you use cylindrical coordinate, and if the problem include rho equals 0, and you solving something involving the Laplacian operator, then likely you get a Bessel function for rho, a Bessel equation for rho. And in that case, you can exclude the y function, y sub n, as k rho or something like that. Because if you include the line on the z-axis, the rho equals 0, then all these functions are singular. We already showed that. And you can just, by the physical requirement that your solution should be regular, then you can exclude all the Neumann functions. So then that also automatically, you see that when you have a situation that you exclude the axis, say you have just cut it out, cut the cylinder out. So, like you have a cylinder of radius A, then you start your solution outside. So you consider the outward, so rho greater equals A. Right? A is not 0, greater than 0. Then and generally if you use a Bessel equation for the radial radial part of the solution, then you need the J sub n and Y sub n. Right? You need both of them because the Bessel equation is second order, so you need two solutions. And that is the one of the situations when you need the Neumann function. But this is it is in principle, but in our homework problem, most likely you won't see that, because that when you involve both of them, then usually the final solution becomes complicated, and likely you need numerical work. The textbook example illustrate one situation. I guess this is a so-called coaxial table. So in this situation, you actually have two. I think you have two. You have two cylinders. So instead of just the inner part, you have this like a metal cylinder at rho equals to A, and then outward you have another cylinder like rho equals to B. The radius is B. Then you want to find the solution within between A and B, the rho from A to B, and like that case, I think is a wave problem, a waveguide problem, and subject to the boundary condition that the solution is 0 on these side surfaces, rho equals to A and rho equals to B, and so that's the decay problem. And sometimes some of these wave move also satisfy the Neumann boundary condition also, that getting even more complicated, but the principle is the same. And in that case, you need the combination of J and Y for a given n, for given order, as well as satisfy the dispersion relation, because it's a waveguide. So the waveguide has a dispersion relation. It's given by 14.73. That also involving a propagating wave along Z. So you have either IKZ. Actually, your textbook use LZ. So you have also propagating along Z also, but the combination of the wave number L and then the wave number in this situation, I think your text will use gamma, but doesn't matter. You satisfy the dispersion relation, so it's omega squared. Square equals to gamma square plus L square. So this is combined like the wave number square equals to the omega square over C square. That That's a common dispersion relation for electromagnetic waves. And that then you need a combination of y and j are 0 on both rho equals to a and rho equals to b. And in that situation, you get to two equations, 14.74 and 75. And that to find the coefficient, that's actually the ratio of the coefficient because these are waves, they're linear solution. So you have a one arbitrary amplitude. So, and this has to satisfy both equations. To find the coefficient, then you need the determinant to be 0. So in that case, determinant, so it's m is gamma a, is m, y is m, gamma a, and j is m, gamma b, y is m, gamma b equals to 0. That you see that the gamma a or gamma b are not the root of either j or m. So unlike what we did before, is we require that the argument at on the side surfaces. So this the argument evaluated at the rho equals to either a and b would be the root of the Bessel function. But in this case, it's not. You need to actually solve this equation for all the possible value of gamma. Solve them, and then sum over all these possible value. And for each value, you should use the dispersion relation and get an L. Right, and so that's a lot of sum. And then this equation obviously is difficult to solve. You need to solve it numerically, and which is possible. It's not. It's just a lot of work to do that. But anyway, that's this illustration how where in a situation you need the Neumann function. That also show that it's usually is much more complicated. Is that okay? So that's the final part. Is there any question on this Neumann function? Another usefulness of Neumann function is to define this Hankel function. And the Hankel function is just like what we call this combination of cosine and sine get you the exponential function, e to the I function, and that using the Euler relation. And those functions are useful for wave, describing wave, right? Because if you combine the usual sine, time dependent, e to the I omega t, you have like this wave, or e to the minus I omega t. And you want to have an exponential function to describe the wave that propagate in a single direction, either positive direction or negative direction. So, so the Hankel function has that property. Okay, and so we'll go to that. I think that's all for the Neumann function, except now we go to using the Neumann function to define this Hankel function.